We want to find the curl of the given vector field. Before we do this though, let's talk about what the curl of a vector field represents. The curl of a vector field measures the rotation or spinning effect. If the vector field F represents a velocity field of a fluid flow or windstorm, the curl measures a tendency of something to rotate in the fluid or wind. The curl of F points in the direction of the axis of rotation, and the magnitude represents the strength of the rotation or how fast it would rotate. The direction of rotation can be determined using the right-hand rule. There are several ways to express the curl of a vector field. If the vector field F has components P, Q, R, then the curl of vector field F is equal to del cross with the vector field F, where del is the differential operator shown here. So this cross product would give us this 3 by 3 determinant. If we evaluate this, we would get this formula here for the curl of the vector field F. So going back to our example, P is going to be equal to y x to the sixth, or x to the sixth y. Q is equal to x z to the fifth, and R is equal to z y to the fourth, or y to the fourth z. So the 3 by 3 determinant will have a first row that's the unit vectors I, j, and k. The second row are the differential operators, the partial with respect to x, the partial with respect to y, and the partial with respect to z. The third row is going to be, let's write this as x to the sixth y, x z to the fifth, and let's write this as y to the fourth z. And now we'll evaluate this using the expansion by minors method. So for this first 2 by 2 determinant, we eliminate the row and column of the I vector. So we eliminate the first row and the first column. The remaining elements give us the elements for the 2 by 2 determinant here. So we have the partial with respect to y, the partial with respect to z, and then we have x z to the fifth, and y to the fourth z, times the I vector minus, for this 2 by 2 determinant, we eliminate the row and column of the j vector. So we eliminate row 1 and column 2, which gives us the partial with respect to x, the partial with respect to z, x to the sixth y, and y to the fourth z, times the j vector, plus, for this last 2 by 2 determinant, we eliminate the row and column of the k vector, so we eliminate row 1 and column 3. So we have the partial with respect to x, the partial with respect to y, x to the sixth y, and x z to the fifth. And now we'll evaluate these 2 by 2 determinants. So the curl of vector field F is equal to, remember for each 2 by 2 determinant, we'll find this derivative and then subtract this derivative. So for this first 2 by 2 determinant, we'll have the partial derivative of y to the fourth z with respect to y, which should be 4y to the third z, minus the partial derivative of x z to the fifth with respect to z, that would be 5x z to the fourth, times the I vector, minus, here we have the partial derivative of y to the fourth z with respect to x, that'd be 0, minus the partial derivative of x to the sixth y with respect to z is also 0, times the j vector, plus, here we have the partial derivative of x z to the fifth with respect to x, which should be z to the fifth, minus the partial derivative of x to the sixth y with respect to y, which should be x to the sixth, times the k vector. Let's write this in component form. So the curl of vector field F has an x component of 4y to the third z minus 5x z to the fourth, a y component of 0, and a z component of z to the fifth minus x to the sixth. Now let's take a look at the vector field F and the curl of vector field F graphically. Notice how both F and the curl of F are vector fields. So here's the graph of the vector field F. We can think of this as a velocity field where these vectors represent the velocity of a windstorm or a fluid flow. And now let's look at the curl of the vector field F. So here's the curl of the vector field F, where these vectors represent the tendency of something to rotate in the fluid flow or windstorm, where the vectors line up with the axis of rotation, and the magnitude of the vectors represent how fast something would rotate in the wind or the fluid. And the direction of rotation can be determined by using the right-hand rule. Now let's look at a single vector in the vector field F at this red point, as well as the curl at this red point. So here's one point in space, and this gray vector is the velocity vector from the vector field F, and this blue vector is the curl of the vector field F, again at the red point. So if this point was in a windstorm or a fluid flow, it would move in the direction of the gray vector, but rotate along the axis given by the blue vector, and how fast it would rotate would be determined by the magnitude of the blue vector. Looking at this one more time, because the blue vector is the curl of the vector field F at the red point, the red pointer-red object would rotate about the axis pointing in the direction of the blue vector here. The magnitude would indicate how fast or how strong it's rotating. To determine the direction of rotation, we can use the right-hand rule. If we point our thumb in the direction of the blue vector and then close our right hand, this tells us the direction of rotation is this direction here. I hope you found this helpful.